Alright, here's actually a calculus problem. And it's at the end of the chapter. They give it's beginning of the question section. And then they give you the answers at the end of the question section. So this is the picture. I didn't. So let's see. Oops. Here it is. You can't see all of it. Without the rubber. Oh, goodness gracious. Okay, anyways. Let's see what we got here. So, we can turn this into a one-dimensional problem because of the symmetry, or at least for the integration. So we have to define an infinitesimal, and remember our general solution is rho times the volume element. So for a rod, a volume element would be pi r squared times dx. And so an expression for rho then would be the whole volume of that rod, which would be pi r squared times L. And let's see, density is mass divided by volume, So then that's going to be capital M, they're calling it. Okay. So that's going to be our rho, and that's our if our dV. So we see that we're going to have capital M pi r squared times L times pi r squared dx. And the limits are, if we can pick this as our origin here, as it's sort of implying, so that means it's going to go from negative h up to L minus h. Okay. And it looks fairly straightforward. It's just going to be then the integral of minus h to L minus h. I guess some cancellations. Whoops. Right, because r is a constant, we're allowed to do that. Well, we could have done it anyway, but we just might have had to integrate m over L. Nice. And something doesn't seem right. Let's see what I got here. Rho times the pi r squared times dx, and then kilograms per, So dx, okay, what am I doing? Something doesn't seem right, because it says x cubed over 3. r squared rho dv. So why is it oh, duh, because I'm calculating the moment of inertia, not the center of mass. Duh. So I just started with the wrong equation. R squared rho dv will get me the mass, and I need oh, I have to be a little careful here. That would be capital. We call it a capital R. I better pause this. I always mix up 1/2 I omega squared with mr squared. So I is equal to mr squared in its simplest form. So rho dv will get us the mass, and then there's the r squared. And in this case, that's some dimension there. So and so we're gonna, instead of using x, we're gonna use r. So then that's r squared, and that's dr. And then yeah, we need to use the capital R because I'm using r squared for something else, and little r squared, and we gotta clean this up a little bit. So lots of shit cancels out, and so r squared dr, and that's equal to m over 3l times r cubed minus h to l minus h. And so m over 3l l minus h cubed minus h cubed, and yeah, there it is. And so it's a bit of a whopper, l minus h cubed. So at first I did these two guys, and then I multiplied it by l minus h one more time, and then we can do this minus h cubed. So you get some cancelizations. Well, one cancellation, then the L, you factor the L through, and you end up with this, which matches there. Nice. And then what's next? B. It is a given constant. Find how much work is done on a rod and times t. So delta ke is going to be 1/2 I omega final squared minus 1/2 I omega initial squared, but it says that's 0. And then if it's constant, yeah, we can substitute. So omega equals omega 0 plus alpha t, that's 0. So then we can substitute that into there. And so alpha squared t squared, I suppose, right, we could simplify it. You know, when it comes to problems where you don't plug any numbers in, and then it's a toss-up as to what's simpler, this expression or that. You know, you still need to know what L and H are, so I would argue, well, no, either or, but you have to go to a lot of trouble to reduce that down to this expression down here. Yeah, nobody goes from here to here. That's okay, so what's the last one? C. At time t, what is the linear acceleration of the point on the furthest from the axis? So that's way out here. And so that one's easy, the tangent alpha r. L minus, yeah, is that the form of the answer? Oh. So what did I do wrong? Let's see. Whoa. Why? So what's the work? L minus H times alpha. Yeah, I'm missing something there. Why? Given a constant round the axle, find the work, how much work is done in the rod. Okay. Okay. Yeah, alpha squared t squared because a alpha t squared. Okay. But oh yeah, you can see that if I make little h equal to 0, I get this. If I make little h equal to 1/2 L, I get the same this. Okay, but I still am wondering about this. Where did that come from? Let's pause for a moment. Okay, so I do this all the time. A equals, excuse me, A tangential, excuse me, plus A perpendicular, and so they're both vectors. So we have to get the total, we have to add them in quadrature. So a perpendicular equals omega squared r. So that means that if we have a constant, that means alpha squared t squared r. So now just add those in quadrature. So that's let's see, L minus h times alpha squared plus alpha squared t squared L minus h. Yeah. So that's L minus h. And so L minus h squared let's see. So let's see what we got. Alpha squared times L minus h squared plus alpha to the fourth g to the fourth L minus h squared. Right, so we can pull out an alpha squared, and right, so we pull that out, so that's alpha times L minus h, and so we had 1 plus alpha squared. We're pulling an alpha squared and L minus h squared out from under the radical, so then they drop their squareds. T to the fourth to 1/2. Yeah, I don't expect it to be a constant because as it goes faster and faster, it needs more and more of a perpendicular component to maintain that rigid body motion. Okay.